Stellar Variability by Professor Don Pollacco from 11:30 to 12:15. Then from 12:15 to 12:45, we have Computational Modeling of Transit Timing Variations by Jack Lloyd Walters, and then a lunch break until 2 o'clock. So Don, may the force be with you.
Can you hear me all right?
Yes, that's fine.
Yeah, okay.
Yep, hear you okay.
So I'm Don Pollacco. I'm from University of Warwick, formerly Belfast. I was the PI for the WASP project, co-PI for NGTS, and I'm currently the science coordinator for Plato. So those are all my exoplanet credentials. But the last few years, I've actually spent as much time working on space junk, and it's led to something really quite impressive, which I'm very excited about, which is a whole sky monitoring system to 21st magnitude every 400 seconds or so, which can be used for real-time supernova detection and things like that. But that's in the pipeline. I hope you'll hear more about that in the next few years. And Plato you will hear about in the next 3 years. Anyway, so today I'm going to talk about stellar activity. And it's really an important factor if you really want to try and understand the planets that you think you're looking at. Before I start, I just want to point out, this might sound a bit pedantic, but I can't help myself, right? And that is that we have 5,700 or whatever planetary candidates. The likelihood is they're not all planets, they're candidates. There's a good number of them that are planets, but to me, you can only confirm a planet if you know its mass as well. And that limits a lot of the Kepler systems. Only the brightest ones could we actually get masses for, and the TTV ones. So, and the reason for this, of course, is that there's a lot of things that can mimic a transit. And the other thing that's really important in this is that if you really do want to understand the composition of a planet, remember you're talking mass over density, and that means r to the cubed, which means any errors in r, in the radius, become really significant. So anyway, I'll just start because I'm starting to talk a bit about this talk now. Hold on. Okay, so I just want to remind you of a couple of things. Everything we're doing is really difficult. Even a hot Jupiter, you don't just walk out into your garden, shove your telescope on a transiting planet and get a light curve. Well, you can get a detection, but this is all about measuring quality results. So in my experience, if you took, say, a Meade 12-inch telescope and put it on La Palma, the state of the atmosphere means you can get a good light curve. Here, then you really need to choose your nights carefully. And I should also just say as well, regarding TTVs, which I'll say more about later, what we found, we did an analysis of a lot of ground-based observations of TTVs, and understanding the errors of the fitting is really important because that dictates the size of the error bars, right? And what that really means is that partial transits are hopeless, and transits where you don't really see enough of, let's call it continuum, either side of the transit, are also very dangerous. And that's because you can't really normalize the light curves very well. Anyway, so because the things we're trying to measure are small, it's never non-trivial, and it's always prone to large errors. And as I said, that has a real implication when you're trying to look inside, when you're trying to get compositions. And as you go to smaller and lower mass planets, then the measurements get even more difficult for obvious reasons. And then the other thing that's really important is that if you talk about transits, if you talk about radial velocities, you're measuring things, relative parameters relative to the host star. So understanding your host star is just as important as understanding the planet. And as an older astronomer now who worked in stars for a long time, I am really pleased because I can remember going to like an RAS meeting in London, and the astronomer royals, who was talking about all of astronomy, said we don't need to talk about stars because we understand all there is worth knowing. And the great thing about exoplanets is that all of a sudden we realized we really didn't understand stars very well at all. So the study of exoplanets has led to a really good, a better understanding of stars, which is really good. And the key to this is a well-used phrase now, but if you want to know your planet, you have to know your star. And as you'll see, it's all about detail. If you really want to produce measurements that are valuable and worthwhile, you need to produce the best quality measurements you can. So I'm just going to very, very briefly talk about discovery. You already heard a lot about it, but I want to talk about it from a slightly different angle. I'm going to talk about spectroscopy quite a lot in this, and about how absorption lines are formed, because that's where you can see keys to activity. So I'm going to talk about how we measure radial velocities, right, and the kind of signals you might expect. I don't think I will talk about the RM effects, the Rossiter-McLaughlin effects. So ignore that one. And I'm going to talk about the sun and activity on the sun, because that's the nearest star that we can study in enough detail. And then I'm going to talk about the effects in photometry and spectroscopy, because we can see these effects, and we can see what the implications are. And then I'm going to talk about what causes activity. So this is I've tried to remove all I don't think there's any maths in this, but I've tried to make it as simple as I can. And then I'm going to talk about what the real effects are on photometry for transits, in terms of what it does to the planet parameters and the effect on timing. And because I'm a Plato person, I have to talk about what is the likelihood of getting 10 centimeters per second. So Rodney mentioned that we have spectrographs that in principle are capable of 10 centimeters per second. And that's right. The spectrographs themselves might be capable of 10 centimeters per second. I don't think that's actually clear cut. I mean, the best spectrograph is espresso on the VLT, which is a derivative from HARPS. And that's just a brilliant series of spectrographs. And the reality with this is that the limiting factor is not going to be the spectrograph, it's going to be the star. So it becomes very important. What is the likelihood of reaching that? And then I'll just say something about bulk characterization for exoplanets in the future. And that's important if you want to identify rocky planets, or if you want to identify water worlds, things like that. So I really like that video you put up of not this system, I think it's HR, whatever it was. And direct imaging is really good if you have distant planets from the star and young planets. And the reason I say young planets is because in those cases, they're actually giving out heat and light of their own as they're still contracting. The likelihood of an Earth-sized object in, say, an Earth-sized orbit is still years away. I got to say that since I've been doing this subject, the Earth-sized detection in an Earth orbit has always been 10 years away. It's still 10 years away, and I suspect it's more than that. It's difficult. It's really hard. May happen with space-based systems in the end. So radial velocity we're going to say more about, but here's a nice little animation so that you can see this is a two-lined binary system. So if you remove the lines in the red star, B, you can see that the A star we still see it. It's moving around the center of mass of the system, as Roger suggested. And so you can produce a radial velocity curve of the host star. And of course, the real implication of this is that the star, of course, doesn't really move very much because it has the greatest mass. If we could make this a double-line system, if we could see spectra from the planet, then the amplitude of the planet's velocity would be completely out of phase with the star, obviously, but a lot greater. It would be huge because it's such low mass. But that's a very difficult thing to do. It's not impossible, let me say that. There are techniques to do it, at least in certain cases. Shall I just say then that you can see the motion of the star, which is affected by the gravitational effect of all the planets, and then you can produce a model to try and account for the motion of the star. So it's pretty indirect. It's pretty risky as well, because what you don't see in this diagram are the errors, right? The errors in the observation. And when you start, and at the bottom, you can see the residual, which means the model minus the observations. And you can see it's not quite on a straight line, but you can also see in the scale on the side, we're talking about hundreds of meters per second, and we want to be at the meter or less level, or preferably much less. So this is a difficult thing to do. And then there's a really, really, really important thing that is often forgotten about, and that is that for all these spectroscopic systems, unless you know the inclination of the orbit, you're measuring a lower limit to the mass of the planet. You're measuring m sin I, right? So what do you really get from spectroscopy? You get that there's likely a planet there. You get the orbital parameters like period, eccentricity, etc. if you have enough observations. You get m sin I. So this is why transits and radial velocities have grown as a pair, because you get I from the transit modeling. So the two together are still the only way to really characterize the planet. So yeah, just to amplify that again, let's have a look at how big these signals really are. We're measuring the motion of the star, remember, as it orbits a center of mass, if it has a planet. And well, let's just see how big these signals are. So here's the answer. And these are now in meters per second. So just remember, the expansion of the universe is measured in thousands of kilometers per second. And now we're talking meters per second. And I've said that an Earth detection is currently not feasible. I think that's, well, I'll believe it when I see it, put it like that. I think it's close. But I know that things at 1 meter per second and half a meter per second are doable, but this is hard stuff. Don't be deceived. This is really hard stuff to do, and you need the most up-to-date spectrographs on the best sites to be able to do this kind of work. The great thing about the spectroscopy compared to transits, which we'll mention in a minute, is that the radial velocity you can measure all around the orbit. So it's not time critical in the same way that a transit is. And it can even be done in less than optimum conditions if you have the right spectrograph. So transits, well, we've heard a lot about that. And here's a well-used animation. And the important thing here is that there's very little physics needed to model this. I say little, there is some. You can see that there's actually a limb darkened star. So understanding limb darkening, which is not trivial, is an important issue, and that affects the size, or rather the shape of the transit. If you go to infrared wavelengths, go to longer wavelengths, then the limb darkening diminishes. So the transit becomes more box-shaped. So if you do a test, say you do a transit at 900 nanometers, you need a good sight. If you could do that, then it looks a lot less rounded, U-shaped than this. It looks more like a box. So if you're trying to measure timing, that's quite a good strategy, because then you're measuring more vertical sides to the transit. The great thing about the transit in the modeling is that the ratio gives you the planetary ratio, size. So you need to know the star radius. But more importantly than that, you get, oh no, not more importantly, just as important, you get the inclination of the orbit as well. So that's really vital, because then you can take that back to the spectroscopy and get the mass. Again, remember, density is r cubed, goes as r cubed. So knowing the star with good accuracy is really important if you want to get a good density for the planet. Finally, timing, and I just put this in because everyone forgets about it. No, there's another one after this, sorry. Timing is really important. This is how the first planets were actually detected, using a pulsar where you could measure the pulses incredibly accurately, and therefore measure the light time changes as the planet goes round, as the pulsar went round the center of mass for the system. And there are error bars on these. It's just that they're so tiny because the measurements can be done so accurately. And that's a free planet system there. I think there are a handful of these pulsar planets known now, so they're not very common. And of course, I mean, who knows how these planets were formed? They could have been formed in the ejector, because this star has gone through a supernova event. Now, I just want to Roger mentioned astrometry, and I just want to mention it again very briefly, because we're just about to enter the age of astrometric detection now. In the next couple of years, DR3 will come from Gaia, and that has a list of confirmed planetary bodies in there. So just keep a lookout for that. And I think the interesting thing will be combining astrometry with, especially, I should say, you can predict which of your astrometric planets could actually transit. So, and they'll be on long orbits, which will be interesting. So you'll have astrometric orbital information. For some, you will have transit detections, and for all of them, you could do radial velocity work as well. So I think that will be a very interesting time in terms of discovery. But let me also, just before I go on, I just want to say something about this this whole field. The danger with the field, especially professionally, is that this becomes a case of stamp collecting. And we have to be careful with this with Plato as well. Most planets are known with such low levels of information that you can't really do very much. I remember the Coro hot Jupiters, for instance, are 15th magnitude. Who cares? Who cares about a 15th magnitude host star with a hot Jupiter around it? No one cares. What's important now is quality. Planets and stars that we really can investigate in detail. And that was one of the main things behind TESS. TESS was launched to find the planets that JWST could do atmospheric work for. That was the most important. That was its reason to exist. So quality now is the really important thing. And what that means, and this is good for the amateur community, is bright. Bright stars with planets are what the name of the game is all about. So you take the Kepler planets, Kepler candidates, only a small fraction of them were bright enough to do the spectroscopy for. It's difficult. Anyway, I just want to say a little bit about radial velocity now. So how is a signal produced? And to do that, let's think about a single line. How is a single absorption line produced? Well, basically, it comes from the whole of the disk. We see an integrated disk. We see the line. You can imagine that different bits of the star contribute to the absorption line. I've shown it as an emission line here, but don't worry, it's the same thing. And depending on the rotation of the star, the line is Doppler shifted. And we see an integrated version, which is basically all of those things shoved together. And we see a blue part of the line and a red part of the line. And it just tells you about where on the disk that component was produced. And that's going to become very important in a few minutes. So how do we measure it? And again, Roger mentioned this, but I just want to show you some real data actually. So how do we measure this signal? So the background is, I don't know which star it is, but it's in a shell spectrum of a star. You can see all the absorption lines. You can see lots of broad lines, which are horrible for measuring radial velocities from, but the really narrow lines are more interesting. So there's a cut of one of those orders. That's actually the sun, actually. And you can see the broad line there. What's that? That's hydrogen alpha. And you can see all these narrow lines around it. So you can see trying to measure the position of that line accurately is not so easy, while the small lines are much easier. Now, the important thing to realize is that if you take 2 pixels on that spectrum there, in velocity space, they correspond. So that's a certain number of angstroms, or a fraction of an angstrom. That corresponds to about 5 kilometers per second. And if we want to measure the accuracy for small planets, we need measurements that are 1,000th of a pixel. So you can't just measure it from one line. You need a system that measures the positions of all these lines, and then basically averages it all out. So that's how it's done, and it's just not trivial to do. And as you'll see, activity will play a part in this. So I'm going to talk a little bit about the sun now. You all know about the sun, but I just thought I would remind you about the sun. And the sun's important because we can look at it in great detail. We can't see this kind of stuff around any other star, but the sun we can examine in great detail. All these things that are going on in this movie here, we can actually measure its position, the time, position, and the velocity that it's moving at, and other things like the magnetic field. That is also incredibly important. So the sun is an interesting test case for us. And so here's some quite old pictures now of the sun. The one on the left, image on the left, is a magnetogram, and it shows that the sunspots are really just magnetic regions. So each white and red, black is a north and south pole, and you can see they're depending in which hemisphere you're in as well. Depends on which side is north and south. So this activity is primarily a magnetic phenomenon, and it's caused by interactions of the magnetic field with the surface material. And I should say, we still don't understand this in great detail. We have a good, I would say, working knowledge of it, but it's incredibly complicated, really complicated. And so we have good measurements of things, basic things like sunspot positions and numbers over the years, and that gives us our 11 or 22-year cycle for the sun. And historically, you can look back and you can see that every cycle is a bit different. So it's a bit floppy in period. They're not all exactly 11 years. They're roughly 11 years. But you can also see times where the numbers of spots is diminished. And of course, in the past, we have this Maunder minima where for 60 years, no one basically saw a sunspot at all. So it's not a predictable, a hugely predictable phenomena, and it's basically related to what's going on deep in the core of the star. And the sun, we can actually measure the brightness of the sun. It's not trivial to do because it's so bright, but what we can see is that the sun does actually vary in brightness if you can measure it like this. So here's shows you the effects of activity. So the top image is the sun over, I think that's the Kepler period, Kepler prime period. So we've got two stars here. Yeah, the bottom object is a Kepler object, Kick object. The top one is the sun measured from something else, but over the same period. And you can see the sun is just moving to an active time. So it starts off relatively quiet, quite small variations, but grows during the cycle. While some stars, like this Kick object here, are just noisy. And so you can end up with a light curve like this. And what we've done here, we fitted a model to the light curve. And the bottom shows you the residual. So what that means is that it's the observations minus the model. And you can see it's removed the variations pretty well, and that's the model with 2 spots. Okay, now the really unfortunate about the thing about this is that almost all activity you see can be modeled by a star with 2 spots. It's really degenerate. The solution is really difficult. So, I mean, when does the sun have 2 spots? Well, occasionally it does. Often it has lots. Sometimes it has none. But 2 spots will model almost everything. So it's really quite hard to get a better understanding of what's going on the disk just from modeling the light curve like that. Oops. So what we do see, well, spots are useful. If they're long lasting enough, we can actually see the rotation periods for stars from the spots. And you see the top one, those sort of vaguely sinusoidal variations are long-lived spot groups on this Kepler object. It does lead to the interesting question: are there any quiet stars? And I think that's a really difficult question to answer, and that's because so far all the stars appear to vary, but I mean, at a very low level, there's always issues with instrumental effects affecting the light curves as well. But there must be some pretty quiet stars. Those could be stars that are viewed pole on, for instance, that for some reason have maybe long periods as well, long rotation periods. But anyway, it's difficult. Here's an interesting thing. So these are spectra of Cen B, alpha Cen B, and the Sun, and they're both G2 dwarfs. Alpha Cen B is always much more active than the Sun. We don't understand why. It does have an activity period, which has been shown in the past to correspond to somebody's idea of when a planet orbited. Let me just rephrase that. So in the radial velocity work, you can get long period planets, or what you think are long period variations, and that can be interpreted as a planet, but it could also be an activity signal as well. So again, you have to be careful, especially when you're pushing to the lowest levels. Now, the interesting thing about this is that even the quiet sun has the same activity indicators in its spectra. So you can see, I mean, you look at that line, the iron line at 4383, and you can see that either side of the main, or what looks like an emission line, there's this broad feature. And you can see in the sun, that's there as well. And during the activity cycle, these things, these emission components change. And where this becomes really dangerous is that if you have an absorption spectrum, which appears to be an absorption spectrum, it will have emission components due to activity basically polluting that line. So it means that measuring the velocity, that you're measuring an absorption line, or what you think is an absorption line, but it's basically contaminated by these emission components. So we need to be smarter. We need to find lines that are less affected by activity, and that work is going on. So we just can't do a blunt way of making these measurements. So there are plenty of signs of activity in light curves, and you can see here, you can see that the spread of lines, the residual, you can see there's a cycle in the residual of these measurements. The middle ones are the calcium 1 lines, that's the H and K lines. You just have to be very careful. The effects of activity are all over the spectrum, even when you can't see a really active star. So in this case, you see the calcium lines, which are often associated with activity, look reasonably flat, but there is activity signals hidden away in this that affect, that you can see in the residuals. Okay, so what causes this activity? So I'm going to talk about 3 things, just briefly: convection on the star, spots on the star, and magnetic fields in general. So here's a 1 by 1K region of the sun for an hour, and you can see these granules growing and then disappearing. And what we have, these are convective cells, okay, and material comes up in the white bits, and then it cools and goes back down to deeper levels in the black bits. So the lines are the intergranule lines, dark lines. Those are regions of material descending, and the white areas are regions of hot material coming to the surface. So you can see you don't need to be Einstein to work this out. You've got material coming towards us, and we've got material falling back away. And whenever you've got motion, in the end, that means a Doppler effect. So these are convective cells, convection on the sun. Now, I should say that it's much more difficult to see this on other stars, obviously. We have predictions that say, I think an M giant will have much bigger cells than this. But really, this is quite an active region. It's because we don't really understand the dynamo very well. That's in the center of the sun. But convection will have an effect. And here's to show you the effect. So on the left here, we have a disk. We have the blue side of this disk and the red side of the disk. So the blue is stuff, the disk rotating towards us, and the red is the disk going away. And what's interesting in this is that if you think about convection, which will be slightly blue shifted because it's coming towards us, and you see where we say upwelling granules, if we could produce an absorption line just of the convective of the white parts, it would look like that. You see it slightly blue shifted because it's coming towards us, while the intergranular lanes, that's the dark bits, are going away from us. So the top, this is from the lanes, and you can see it's slightly red shifted. It's red shifted, and the cells, the white parts of the cells, are slightly blue shifted. Now, if you really do a model of how a line is made in an atmosphere, it's not actually, this has a nice surface, but the cores of the lines actually are produced in the atmosphere of the star. So we just see everything integrated together, okay? So you can imagine if you added these three things together, how complicated it might look. And in fact, this gives you a better idea, right? So what I've done here is I've called this thing the bisector, right? This C-shaped bisector. This shows you, if you were to measure the absorption line and measure the middle of the line, it shows you where bits are produced at different heights. And this we can actually see. The lines are slightly deformed when all of these things come together. And the lines are overall slightly blue shifted because of the convective cells. Now, what happens if you've got a spot? Well, you can see you've lost a bit of light for a start. And so overall, in this case, the spot's in the red part of the disk. Then the red part of the disk is, oh, there's a mistake here, is actually suppressed slightly. So you can see the absorption line here is slightly distorted, with the red part being slightly lowered by the loss of this. But there's also something else of importance that goes on. And that is, if you look around the magnetic regions on the surface, the convection is actually suppressed. So even the convection signal, the red part, the red part of the convection signal is also suppressed by a spot region. And so we see less, we see a more straightened bisector. It's not so C-shaped as it was before. Now, I know this seems like it's, sort of nitpicking, but remember, what we're trying to do is to measure a line to 1,000th of a pixel. So it's not trivial to do. Now, I want to put this in. This is something I teach in second year. And I think it's really exciting, right? So what we have here is a graph of wavelength against magnetic field. So let's start at the bottom here. This is well, this is still a pretty big magnetic field. But what we've got here are the hydrogen lines, the Balmer lines. This is hydrogen alpha, Balmer alpha, beta, gamma, etc. And if there was no magnetic field, well, I'm sure you know what the spectrum would look like. But as soon as you start applying a magnetic field, what's interesting is that the energy levels that produce these lines start splitting. Okay, it's due to their magnetic qualities of the energy levels. And as the field gets stronger and stronger, let's take hydrogen alpha. You can see when you've got, it's already quite a strong field, 100 Teslas at here, and there's already 3 hydrogen alphas. Okay, so there's more than one, there's 3. And as the field strength increases, then you get lots of hydrogen alpha components being produced. And they appear all kind. I mean, you take this one here. So at a field of 100 times 100 Teslas, hydrogen alpha will have a component here, one here at these wavelengths. So you can see there'll be hydrogen alpha component, Balmer alpha components all through the optical spectrum and into the infrared. And so it becomes really complicated. And let me show you what a magnetic star looks like. So what we have here, this is I think this is a strength of 20,000 Teslas. This is the hydrogen alpha line, and you can see there's 3 main components with multiple minor components. This is a model, and this is a real star as well. So magnetic fields are really important, and if it's very magnetic, the activity is really high and makes everything much more complicated. Another issue that we have to be careful about is pulsations. So stars pulsate, the sun pulsates, very small amplitude, but that produces, this is Virgo time series, this is the sun's brightness, and you can see all this noise in here is because of these pulsations that are going on in the sun. The amplitudes of these are small, but they make an observable effect. In fact, you can use them if you can identify the pulsations in the light curve. So if you did a Fourier analysis of this time series here, you would see specific frequencies that correspond to these different types of pulsation. And that tells you about how sound waves are traveling through the sun. Okay, and that can tell you a lot of things. It can tell you what's inside the sun, and that can tell you in the end about how old the sun is or other stars are. So what does this all mean? For transit detection and timing. Well, obviously, more activity, more difficult even to detect transits. For any, the more active it is, the less easy it is to detect a planet of a specific size. And smaller planets get more difficult for any activity level. So activity can basically mask the transits of small planets. So one solution is to observe more transits. In fact, the whole case for the Kepler extended mission was because the activity levels of stars have been underestimated. And to get enough transits of most stars to be able to say you've definitely got one and you know what the period is, meant observing more transits. And then the other thing, of course, is that the transit itself, as I'll show in a minute, is affected by spots and what have you. And that affects the accuracy that you can fit it and has an implication for timing as well. So here's some light curves. It's the Kepler light curve of Kepler 17. And you can see over here, in this case, it's actually been used to map out the spots on the surface of the host star. So here's the transits. You can see this big activity signal. And if you look in detail, here's the Kepler observations in detail for each of these transits. And you'll see that the transit is distorted in this case. So if you think what you're measuring here planet comes on the disk at the ingress here, travels across, and then exits the disk of the star. So halfway across, or almost halfway across, it meets a spot. Okay. And so the position, the distortions in the light curve tell you about the positions of the spots. They tell you about the surface of the star. You can see here there's probably multiple spots in this case. And so you can go through them as like this. I mean, this is an active star, and that's why there's quite a lot of distortions. In a really active star, you wouldn't see the transits at all. So if you could produce a really high signal to noise transit observation, this is actually a model, right? And you can produce a whole series of these with the spot moving across, or rather the planet, sorry, with the planet transiting the spot in different positions on the surface of the star. You get light curves that look like this. And I think the important one here is this blue one, where you can see it's met the spot towards the edge, towards the egress. And now just imagine if this wasn't high signal to noise, would you see that? And what's the implications of this? So here's a few graphs that really try to, these are all based on models, I should say, and show you what the implications. So if we start over here, planet radius, basically you can get it up to a 5% in these particular models here. So we've got RP, so the radius of the planet divided by the radius of the star is 0.15. So that's a hot Jupiter. You can end up with a 5% error just from the transit, modeling the transit when the spot is in the center. Okay. When the spot moves to the side, well, just think what you're measuring. To measure the radius, you're measuring the depth. So the depth is most likely affected when the spot's in the middle of the disk. And when it's on the side, the spot depth, or rather the transit depth, is less severely impacted. So the planet radius in general is not so badly affected. I mean, the good thing is you can see the spots, but timing is badly affected. And that's because as the spot moves to the side, if the star transits the spot as it's towards the limb, then and these are high quality models, remember, then the overall effect can produce hundreds of seconds of error in your transit model. And you also see that if you're trying to measure the duration of the transit as well. And I should say that for exomoons, transit duration modeling is commonly, people try and use it, but it is a very difficult technique to do, and you can only use the highest quality observations. So those are the dangers now of TTVs with spotty stars, and that's why understanding activity of the star you're trying to do this for is I think it's Kepler. I think it's WASP-10 is a pretty active star, and we've seen TTV signals from that, which we think are really just activity signals. For radial velocity work, it is even more serious, and that's because the activity mostly affects some lines, but not all the absorption lines. So the name of the game is to find absorption lines in the end, but you still got to have thousands of them to get the accuracy. Some that don't have absorption or emission components in. And the overall effect of this is that lower mass planets become much more difficult to detect. It also screws up activity. Activity also screws up the orbit determination as well. And so in the end, really, you want them to use the lowest activity stars you can. And even in those stars, you've still got the convective signal to worry about. So you need to take multiple observations and average them out. But that is an incredibly observation intensive problem. And these observations are being done with 10-meter telescopes. I don't know if I might just say something about how, well, I've got a few minutes, right? And the other thing, of course, is that activity works on timescales from minutes, so things like flares, to spots, which are months, to cycles, which are years. So things like flares and stuff you can usually disentangle, provided they're not tiny flares. But longer things, well, if you've got a transit, you might be all right. But if you've got, like in the SEM-B case, if you've got a long period in your radial velocities, that could be a planet, but it could also be an activity cycle. So 10 centimeters per
Another
second.
5 minutes, Don. Is that okay?
Yeah, I'll be finished. I've only got 2 slides.
Right.
So the level of stability is now possible. We can average them to get the right, possibly the right level of accuracy. But really, we really need to understand activity to be able to model it out the light curves. And there's other things we can do, like try and do this at infrared wavelengths where the activity signals seem to be lower. So here's my summary. And I think, well, I'm not going to, I mean, you can read this yourself. I don't need to read this. But what I would say is that you take an issue, you take something like Plato. Plato flies in 3 or 4 years' time. You think of the stars that you're going to select to observe with it. Well, if you select them now, they've got some part of an activity cycle to go through. So quiet stars now are no guarantee in a few years' time. Really high signal to noise photometry has to be used to be able to model the transits. And it also has to be able to model the timing as well. I mean, Plato is built to do transit duration measurements as well, and also transit timing measurements. I think the real issue with activity is going to be in spectroscopy, and we really do need to model it and have a smart way of doing this work. I don't need to say any of this. That's me.
Right. Thanks, Don. Thanks, Don. Could I just ask you a question about the age of astrometric detection? I mean,
Yeah.
I presume there's a few been detected already, but what sort of accuracy could we hope for with large planets orbiting small stars? I mean, we're talking about milliarc seconds, microarc seconds, or what?
Well, it's in between the two, and it's on a case by case. I think the problem with this is that you take something like Gaia. Well, there's astronomical problems. If you put a lot of spots on a star, where's the center of light of the star? Right? Think of that. But it's not the center of the disk anymore. And I think that, but one of the interesting problems, the reason that information hasn't come out already, is that the closer you push the instrumentation limits, the more you find out what the limits really are. And these spacecraft, yes, I think Gaia's at L2, but still there's a certain amount of breathing that goes on the spacecraft that affects at the microarc second level. In principle, before Gaia was launched, people thought we'd be getting Earth mass planets. And I think now it's probably going to be Neptune's and bigger. I think the interesting thing is that the signal basically scales with semi-amplitude. And what that means is that it's actually better for longer period planets. So it complements the transit and the radial velocity work quite well.
Okay, thanks, Don.